Okay, so we're going to kind of pick up where we left off last time. I'm actually going to change my tack a little bit from where we had started last lecture. Last lecture we had started doing thin-walled beam bending, and I realized that that is going to be a little bit harder for you guys to understand than it's going to be a little bit harder to understand if we don't do torsion first in the context of not being together and being able to physically sort of describe some of these scenarios with the props that I usually bring along with me to these lectures. So without those props, we're going to change our order of operations here a little bit. We're going to hit torsion of solid shafts before we do bending of thin shafts, and then we'll get back to that bending problem shortly thereafter. So today we'll talk about torsion of solid shafts. Now this, of course, is covered in the textbook, covered in the course pack. We'll go ahead and get started with it so that everybody can be on the same page. Now, I had a video when we were talking about beam deformation. We recognized and realized that the simplification that comes in doing beam analysis as opposed to doing elasticity theory analysis in its most fundamental is that we were able to observe how a beam deformed based on some geometric observations of what characterizes a beam. And just to remind you, the beam was much longer in one dimension than it was in the other two dimensions. And when it deformed, plane sections remained plane, and they remained perpendicular to this reference line that we had established. And that ultimately allowed us to be able to write an equation for what the beam deformation looks like when it is deforming. So the equation related the centroidal deflection or displacement. Deflection is inherently for a beam at the centroid, whereas displacement could be anywhere in the beam. But looking at the deflection, we were able to write the displacement everywhere in the beam based on some simple assumptions of linear kinematics for an Euler-Bernoulli beam. Well, now we'd like to look at torsion of shafts and make similar arguments. And if we're able to make similar arguments, we will obviously then simplify the deformation calculation for a torsional shaft as well. And in both cases, if you can write these equations for deformation, then you can easily differentiate to get strain, and you can easily apply the constitutive law to get stress, and then you can evaluate boundary conditions. And so it's always easier to differentiate than integrate, and that's what makes these processes easier when we use these theorems, engineering theorems. So anyway, staring at the screen here, we have a straight bar with a constant cross-section where we're applying equal and opposite torques. So really two figures here, one on the left and then one on the right, where we're looking specifically at a cross-section within that beam. Now, before we get into too great a depth on the deformation that occurs in this beam, I'm going to hold up this ruler. Now, why don't you... I know you guys are all able to pin me on the screen, so go away from the slides for a minute and look instead at this ruler. Okay, now this is in some ways a good example of a shaft. Now this actually happens to be sort of a thin-walled beam as well, and our equations work well for thin-walled shafts as they do for regular solid shafts, so I can use this. The reason I picked this up today was because this is nice and flexible. It's easy to deform, and you guys can visually see the deformation, I think, through my camera. Okay, so anyway, the idea here is it's straight. When I say straight, we're talking about the reference line of our cross-section, or actually the reference line connecting our cross-section, so along the long axis of the beam. In this case, when I say I'm applying equal and opposite torques, I don't know if you're able to see both my hands from where you are, but you can basically see that I am twisting on one end, twisting the opposite direction on the other end, and therefore we're deforming this ruler, and we're deforming it in a torsional mode so that one end is twisting rather relative to the other. Now, we're going to, much like we had to do when we were describing beam bending, we had to pick a reference line. In beam bending, we picked the centroidal axis as our reference line. In this case, we're going to pick something called the center of twist. Now, just keep that in the back of your mind, and we'll develop what that is in a minute. Now, I've moved my slides ahead, but again, I'm going to ask you to focus mostly on the deformation that I'm showing you with the ruler rather than on the slides, and then I'll give you some time to digest the slides once I'm done demonstrating the ruler. In fact, what I'm going to do with the slides is I'm going to highlight one image here for a moment. That's this image. And I want you to envision that cross-section. In this case, we have a cross-section. It's of arbitrary shape. It's not circular, elliptical, square, or anything convenient like that. It's just a random shape. We'll have a point where we're going to put our XY coordinate system. We're going to call that the center of twist. And then in a little while, we'll actually identify where that is. And I've identified a couple of points on here, one called P and the other called P prime. So I've got a point on the cross section that moves as I twist this. Now, go back to looking at my ruler here for a moment, and I want you to watch the end. I'm going to try and hold one end fixed, and I'm going to try and twist the other end without bending. Now, you have to imagine, and it probably doesn't have great optics coming through the camera, but I'm going to twist this beam. Ignore any bending that I might be putting into it. Instead, just focus on the twisting. Now, what we're observing as I twist this, and if you happen to have a ruler at home, I encourage you to get it out of your desk and play along with me as we do this. What we're seeing is that at a point P, and for the moment I'm going to say the point P is at the top of my ruler. At a point P, it has a displacement that occurs as I twist it. Now, I'm going to hold my ruler at an angle, okay, so it's not straight up and down. It's now at roughly a 45-degree angle. As I twist my ruler, you see that the point P moves in plane. So this is in the normal plane to the cross section of the ruler. The point P moves both in the X and the Y directions. So relative to where you are, if you're looking at this top corner, the top corner is moving up, so that's a positive V displacement. And depending on whether I'm mirrored or not, I believe for you it would be moving to the right, although I guess I'm not 100% confident that that statement is true. Now, so what we observe as we twist this thing, we get deformation. We get a displacement U and V. All right, I'm going to set down my ruler for just a moment, and I'm going to highlight this in the slide. So the in-plane displacements, of course, they are U and V because they're in the X and Y directions. They are going to be 0 along the center of twist, and otherwise in that plane are going to be non-zero. Now, what do I mean by 0 along the Z-axis? Again, I'm going to hold up my ruler. As I twist it, you see the top is going, say, up and to your right, I assume to the right. The bottom is actually going down and to your left. And somewhere here in the middle, as I twist it, there is a single point that is not actually moving because it's the rotation is occurring about that point. So at that point where the deflection is 0, we're going to call that the center of twist. We're going to make that the Z-axis of our reference coordinate system. Now, the next thing, and it's shown up here in the diagram, I'm going to emphasize it with much bigger lines. We've got an angle alpha that is the amount of twist, the total twist from one side of the ruler to the other side of the ruler. So in this case, I'm twisting this thing on the order of about 15 degrees. Okay, so alpha is 15 degrees. We're going to call that the twist angle. And again, it's the total angle of rotation. Now, it's along the z-axis. It changes. Alpha changes the further you go down the axis. But this, of course, has to be measured from a specific position. So, you know, for the time being, I'm going to say it's measured from what is my left hand that's holding the ruler fixed at one end. The total angle of twist is at the right end. But this ends up being a relative magnitude. So we could have fixed it here in the middle and still had a total twist. And really, in the end, what we're going to find is that the amount of twist that occurs is important. But what's more important is the so-called rate of twist. That's how much twist occurs per unit length in the z direction. Now, the next thing I want you to do is to recognize that we've talked about the in-plane displacement. So that's u and v. Those are the displacements in the x and the y direction. Okay, we obviously have three-dimensional structures, so the third dimension can also have a displacement. We're going to call that displacement w, so we're going to call it the warping. And we're going to, first of all, say a couple of things about that. Okay, the first one is I actually need you to do this other exercise now. That exercise is to pick up a piece of paper because I want you to see precisely what warping is. Okay, now I have my piece of paper. I'm folding my paper around on itself, so I'm making a hollow cylinder. This paper is a little bit stickier than I anticipated. Okay, so there I have my hollow cylinder. Now, you can see, I hope you can see that, again, we have a point that's readily identifiable here as the corner of the paper. Now, note that the warping that we'll see will be relatively obvious in this sheet of paper, which is why I'm using it. It's not as obvious in the ruler. Okay, so the next thing I want you to do is I want you to twist your sheet of paper, and hopefully your sheet of paper is less sticky than mine. Okay, and what happens as you twist it is that you get the corner of that sheet of paper will either move forwards or backwards, depending on which direction you are twisting this sheet of paper. If we turn the sheet of paper sideways, you can see that this is now a warped sheet of paper in the plane. The plane itself, the original plane, is warped. Okay, that's why we call it warping. Now, another thing that's interesting is if you take 2 points that start at the same spot, so if I were to hold my sheet of paper sideways here, and I had a point here and a point here, okay, front and back, they started at the same XY position in the cross section. So in this case, they're both front and back are at the top side. As I warp my sheet of paper, so I have twisted it, okay? In this case, I twisted it in such a way that the sheet of paper, the corner actually moved towards me as I twisted it. And what you note is if I stick the other end of the sheet of paper up in the sky, you can see that also moved towards me. So what we're observing as we twist this shaft, and similarly, you would see it would be quite similar, in fact, with this ruler, although, of course, the amount of twisting is much smaller. That's why I chose to use a piece of paper. What we're seeing is that the projection of the warping onto the XY plane essentially moves as a rigid body. So the same point, in this case, we were using this point P. If it warps and it comes forward on one end, it's going to come forward on the other end, and vice versa. If it came backwards on one end, it would go backwards by the same amount on the other end. That's, of course, assuming that we have a straight shaft of constant cross-section with equally applied torques at both ends, opposite directions. Okay, I'm going to pause there and take any questions. Are there any questions about what I'm saying?
Unrelated, but what's your favorite aircraft?
Who asked that?
That would be me, Joel.
Joel, great question. So to be honest, I'm going to accept a number of answers for that because my favorite aircraft changes from day to day. I would argue that my absolute favorite aircraft of all time is probably the Corsair, World War II era fighter. Absolutely a beautiful airplane. If you've ever seen one fly, or more importantly, listen to one fly, that is the sound of freedom. But there's no way you can choose just one. I would choose the Skyhawk because that's what I fly on a day-to-day basis. I would accept the F-22 Raptor as the dominant fighter aircraft in the sky anywhere in the world today. Basically any one of those would be acceptable, probably a couple of others as well. But yeah, let's get back to the lecture. So any questions about
questions? How does warping happen in the ruler? I can see it in the paper, but how does it happen in the ruler? There's nothing sliding against each other, is there?
Well, that's a great question, and it's honestly a tough question to answer with the props that I have available to me right now. Honestly, the best way to see this, David, would be to do an experiment. Go to Home Depot. At Home Depot, they sell insulating foam for pipes. Okay, so your water pipes probably in your basement come in. The water comes in cold, and so there can often be condensation. And on those pipes, because they're then exchanging heat and locally cooling the air surrounding them, and it brings the air, the relative humidity locally around the pipe to 100%, and then you get this condensation and moisture, of course, and that can drive mold. Also, the other argument for insulating your pipes is you don't want to spend energy heating the water that's coming into the house if you just want it to go down the tap as cold water. So anyway, so go to Home Depot, buy yourself some of that insulating foam. The insulating foam is a circular cross section. It's hollow, but it's also got a split in it. And when you buy it, you probably need to take your finger and actually activate the split, open it up. Oh my goodness, I probably have insulating foam in my basement. Let me go steal it from my pipes. Give me just 1 second here.
You got so excited about that phone just now.
I bet his wife is like, what the hell are you doing?
All right, hot off the presses, here we go. I stole some, this is what that looks like. Just insulating foam. You can see it's got this split. Okay, now as you twist it, you're going to see this. Let me turn it sideways. You can see it very directly. See this little gap that forms as I twist it, untwist it, twist it. So when you have cross sections like this one that have some sort of asymmetry, it tends to be much more visible. Okay, and we'll get into the mathematics of that in just a few minutes. In this cross section, you would actually see a little bit of that warping if you looked at it close enough. If you could exaggerate the z direction displacement, you would see some warping in this rectangular cross section. However, you actually don't see warping in all cross sections. A perfectly circular cross section or a pipe like this, if it didn't have this slit, it would twist without warping. Okay, so why does it occur? It's the mathematics of the problem. It ultimately comes down to energy minimization. But the best way to physically experience this is to experiment with a couple of things. So go buy this at Home Depot to play around with it, or if you have a swimming pool noodle, that's another good one. I like to use the noodles. That's actually what I bring to class, is a swimming pool noodle, because it's nice and big and long and visible from the back of the lecture hall. Okay, so anyway, again, I kind of got to get back here on my game. So cross sections can warp. Yeah, the projection onto the XY plane rotates as a rigid body. Any point that starts at the same point in the cross section as it warps is going to move the same direction, either forward or backward. And so what we're saying here is that the W displacement is assumed, because of this observation, to be independent of Z. Okay, along the Z-axis, the warping is the same at any point within the cross-section. Now, the next thing that we can define is the amount of twist per unit length. Okay, so as I twist this thing, it's a little hard to see maybe. In fact, now that I have this pool noodle, this is probably better, except you don't have any contrast with that. Okay, I'm
going on with the whole twisting thing. So when you were showing the pool noodle, you could see the warp from one side to the other, but that's also right across the split there. So the ruler's not going to have a split. Like, is there going to be a point where, right next to each other, one is significantly warped from the other, or how does the warping work in something that's not split?
So, I mean, that's a great question. And the answer to it is that it's much more visible because this split exists. And because as a result of that, I mean, what we're doing is we're applying a shear load. Okay, the bottom line answer is we're applying a shear load. Shear load is what torsion comes from. What happens when something torques? Okay, when it shears. If you go back to elasticity theory, very first couple of lectures of the semester, I said that normal strains are extensional strains. They can change volume. They certainly change length. Whereas shear strains are angular changes. So what you see here is when comes down to a shear problem, we see a large angular change, and that angular change is most dramatic in this cross section, because 2 points that were otherwise adjacent to each other but are not bonded to each other slide past each other. Now, having said that, if they are bonded to each other, if it's a circular cross-section, the mathematics will mean that they don't warp in that direction. But if it's a non-circular cross-section, if I squish this thing to be an ellipse first, and I glued it together, and then I twisted it, you would see warping in an ellipse. Okay, so this is something, again, I would just, I don't want to just say trust me. I mean, the mathematics govern it, and we'll get to the mathematics in a few minutes. But you can physically experience this yourself. Okay, so anyway, bottom line is, if we look at the total angle and we divide that by the total length, we're going to call that our twist per unit length. I also refer to that as the rate of twist periodically. Rate's not the great word, because rate could imply time derivative, but really when I'm saying that, I'm saying derivative per unit length. So even though it's expressed here as a total angle over a total length, you should really be thinking of this as a derivative. It's a rate per unit length. Okay, now when we've done this, we can actually, and let me zoom back, I'll zoom back in here in a moment. We're going to look here at this image, and what we're going to see is that the U displacement as it moves will move by an amount that's proportional to the angle and then it also happens to be proportional to its initial position. Okay, same for V. So it's going to be proportional to the angle and its initial position. So its initial position is defined really by two terms. It's R and beta of this other angle. So let me go ahead and zoom in on this image so that you guys can see what I mean. Unfortunately, I lose my ability to write on the image when I zoom in on the image like this large. But you can see its initial position, XY, can be defined by the radius R and the angle beta. So that's an initial position of point P. X and Y are defined by R and beta. As it twists, it moves. That movement is proportional to the angle alpha, and it's also proportional to the position XY. Now, we can imagine if beta was 0, we'd be talking about a point out here at X. In fact, let me go back, and I'm going to sort of redraw because I think this is a good thought experiment. Okay, here's my arbitrary cross-section. Here's my X and Y axes. If my point were here and I swept through an angle, it would move this direction, and the initial component would be entirely vertical. If I use this point and now it's sweeping through this angle, then that component is entirely horizontal. And so you can see this angle beta now is something that matters. If you're somewhere in the middle here, if this is your initial position and now it's moving this direction, it's now somewhere in between entirely vertical and entirely horizontal, and that is governed ultimately by this property, this geometric entity, R sine of beta.
Professor, I have a quick question.
Yeah, is that Jeremy? Go ahead.
Yes. U and the vector that's being defined by U and V in the picture, is that supposed to be the displacement between the 2 points?
Yeah. So P, the point P, which is at this intersection here, as you go sweep through angle alpha, P moves from P to P prime.
Okay, so P prime isn't on the radius of the
Yeah,
shape.
you know, this is not a perfect image. It ultimately it comes from the textbook, really, but no, if going back here for a second, let me go to the blackboard. If this was what my cross section looked like, okay, and this was my initial point P, it would move up in this direction, and then this is my initial my new point P prime. Obviously, it's not on the surface as it's rotated. What I think maybe you were being confused about was, what were we talking about, this point or this point? So it's P moves from P to P prime.
Okay, yeah, it just has P prime like marked weird then. Okay, thanks.
Yep. Okay, and obviously R sine of beta and R cosine of beta are simply X and Y. And alpha, as we've defined it up here, is now going to be, we can substitute in z theta, so we can multiply this equation here by z, and so we get z theta is equal to alpha, and so u and v now are going to be equal to these terms. That is theta times z times the position, x or y, and then you get a positive or negative sign based ultimately on, again, it goes back to this image, where you can see for a positive angle alpha, the point P moves negative u, right? It moves an amount in the negative direction. So there's this positive negative thing that occurs, and so that's where we're getting this negative sign from in the equation. Okay, so we've already stated that the warping, that's the W displacement, we said it was independent of Z. That means at the front and the back it moves the same amount. right? And what we also would observe as you do this is it's proportional to how much twist you've applied. So the proportionality constant is simply theta. That's the rate of twist. Now it's going to be times something. Here we're filling it in with phi. Phi is in general a function of x and y, so that defines for the different points in the cross section how much they move. It is a function of x and y. It's independent of z. So that's really important to recognize. We've said that a couple of times. I'll continue to emphasize that. And again, this thing phi, we're going to refer to it as a warping function. Now, so in summary, what we've done is we've observed something about the deformation that occurs in the cross section. We can relate it to the overall amount of twist that occurs. Really, it's a rate of twist thing, and then you integrate over the length of the domain. So it's proportional to the rate of twists and has to do with your position within the cross section. Another really critical thing is once we have assumed this, we observe it, we state those as assumptions. Once we make those assumptions, actually it turns out that we can compute strain, and several of the strains are identically equal to 0 by definition. Let me show that to you. Okay, what I have here, these top lines are simply the equations of deformation that we've already assumed based on what we observed. I'm also writing down 4 of our 6 strains. Okay, the first 3 are all normal strains. So epsilon xx is by definition du dx. That's the kinematics that we observe. Here's u as a function of x up here. You note that x is not present there. We've got the rate of twist, and we've got z and y. So the derivative of that is going to be equal to 0. Similarly, we can look at epsilon y. This is dv dy. Here's v, which is a function of theta, z, and x, not a function of y. So epsilon yy, again, 0. Epsilon zz, by definition, dw dz. Rate of twist, which we've, by our assumptions here, defined as being a constant along the length. It's at least constant along a differential length, times now our rate, or I'm sorry, our warping function, phi. The warping function, by definition, is only a function of x and y. So z does not live in these equations here, and ultimately dw dz becomes 0. Now there's one more that we can pay attention to, and that is gamma xy. So this is the shear on the x face in the y direction or the y face in the x direction. Symmetry defines those as being equal to the same. By definition, this is the kinematics, du dy plus dv dx. Well, here's u again up at the top, right? So this one's u. We take the derivative of that with respect to y, we get theta z, and it's negative. Plus dv dx, we take the derivative of this with respect to x, and we get theta z, and it's positive. So minus plus the same quantity obviously is going to be equal to 0. So here, by observing these things about the deformation of this twisting structure, we can identically immediately remove 4 strains from consideration. 6 strains in total, 4 are 0. We've already made this 2/3 easier. Questions? Okay. Now, for the moment, we're going to assume that body forces are 0. Okay. by the way, so the equilibrium equations that I've written here, I've already shortened the equilibrium equation just to remind you what was present here. So this is this is actually now the third equation. So the third of the three equilibrium equations, I'll write out the entire thing here. So sigma xz comma z plus sigma yz comma y plus sigma zz comma z plus the body force in the z direction plus the is equal to rho times the acceleration in the z direction. So this is the third of those three equations. What we find is because the zz strain is 0, this one goes away. We're going to neglect body forces and we're going to neglect accelerations. It isn't strictly necessary that you neglect those. However, there's a pretty good argument for it because ultimately body forces are better treated by beam bending equations. It's rare that a body force would cause a torsion in and of itself. And so we're going to, much like we said, axial deformation becomes decoupled from bending, except in some specific circumstances. Here again, we're going to see that torsion becomes decoupled from deformation if you're tracking your equations correctly. So we'll go ahead and do that. We'll just assume this for now. It makes the math a little bit easier. And we can touch on that again more if somebody would like to ask questions about it. Anyway, so what we have left of all those equations, all three of the equations, really only one of them remains, and that's this one. The others are identically equal to 0. Okay, so this simple equation is what we need in order to have equilibrium, that is stress equilibrium hold. A guy named Prandtl introduced what he defined as a stress function. Now, we don't know what that stress function is. However, he said, all right, well, looking at this equation, if I can write a function phi such that its first derivative with respect to y is equal to tau xz, and minus its first derivative with respect to x is equal to tau yz, then if we plug that into the above, this will be identically satisfied. So we don't know what it is. However, we know if this holds, it satisfies equilibrium. I'm seeing what was Tyler asked a question. If I wrote d tau xz dz on the slide, that was a problem with writing with a mouse rather than a pen. My z must have looked, sorry, my x must have looked like a z. So apologize about that. Thanks, Ethan, for answering it for him. Okay, so anyway, that's what we're doing. We're going to try, now one of our challenges will be to find this function. We don't know what it is. We got to figure out what it is, but if that function exists, we can automatically satisfy the equilibrium equations. Okay, we also know this is by definition of strain. So this is the strain kinematic equations that we developed for elasticity theory earlier. That the definition of the shear strain xz is nothing more than dw dx plus du dz. The shear strain yz is dw dy plus dv dz. And furthermore, we happen to know that we can write, based on our assumed deformation, the values for u, v, and w. Okay, so I've plugged in the values, that those equations that we wrote for u, v, and w. I've plugged them now into our strain equations. Okay, and so they're relatively simple here. We see that one is a function of x, one is a function of y. We still, in each case, have still this partial derivative of w with respect to x or y present. We also note this sign change that comes up because of that negative u that we showed in the diagram. Now, we can then manipulate these equations. This is just plain old mathematical manipulation. You can do kind of whatever you want as long as you're not violating math, right? So here I'm going to, for example, say, all right, I know what gamma xz is. Let me take its derivative with respect to the y direction. And what results is this, partial square w, partial x, partial y, minus theta. Similarly, we take a derivative of the second one, but now instead with respect to x, and we get partial gamma yz partial x is equal to partial square w partial x partial y plus theta. What we're ultimately trying to do is combine these equations into a useful tool. And the way that this is now expressed, you can see that we're getting pretty close. These last two equations, if we subtract one from the other, so for example, if we subtract this one from this one, these equations here are just carried forward from the last slide. So if we subtract one from the other, what we end up getting is this equation. That is d gamma yz dx minus d gamma xz dy is equal to 2 times theta. Now, mathematically, that's not terribly difficult to accept. We can handle that, probably could have handled that many years ago in your mathematical training. However, we would like to have a physical interpretation of what this means. And what we're seeing here is we're relating the amount of strain that occurs, actually in this case, its derivatives, to the rate of twist that is present. And really physically what this is this is the compatibility equation for torsion of the shaft. And if you remember the compatibility equation, or the concept of compatibility from earlier in the semester, that is that we don't form cracks or voids, that 2 points starting together need to end together. Now I want to make sure that you're clear that, when we have this foam structure, you might say, well, Dr. G, when you twist it, those 2 points started together, but they moved. But they were actually two distinct points. They were separated by the slit that was put in the foam. We're not creating a new void that wasn't there before. However, if these 2 points up here, this is at the other end, the opposite end of the split, they cannot form a new crack or we've changed the problem, right? So this equation essentially says that deformation needs to be compatible. You can't form new cracks or voids. You need to have single-valued displacement functions. Okay, now separately, let me just check some boxes here first. If you recall what we said we needed to do with elasticity theory is we needed to, there was that chain of relationships that needed to functionally work. So we had a displacement field through strain kinematics gave us a strain through the constitutive law gave us a stress, and the stress through the Cauchy equation and the definition of the traction meets the traction boundary conditions. So amongst all of those things, so far we satisfied equilibrium. So that's the stress equilibrium equations. We satisfied kinematics through this compatibility requirement. So the next thing we need is the constitutive relationship. So that's what's showing up now on this slide. It's our constitutive relationship. By linear elastic definition of our constitutive relationship, so this is for a linear elastic isotropic material, we have a parameter G called the shear modulus. As you recall, it's related to the Young's modulus and the Poisson's ratio. but we're going to use the shear modulus here because it's much more convenient. So the total strain is 1 over G times the stress. Shear strain is equal to 1 over G times shear stress. And we can then just take this equation and plug it into the prior equation. That is this equation. And that leads us to now this equation. So the first derivative, I should say, partial tau yz partial x minus partial tau xz partial y is equal to 2g theta. Okay, now, so what we have is, again, a stress related to a rate of twist. And don't forget that that guy Prandtl suggested, oh yeah, well, here's something, I don't know what the function is, but if this function exists, we can satisfy equilibrium. So we can apply that stress function into this equation. And when I do that, this is what arises. That is partial squared phi partial x squared plus partial squared phi partial y squared is equal to minus 2g theta. Okay, so we did a lot there. We went through at least a half dozen equations. All of these equations, again, based on this assumption of the deformation that we observe by actually twisting a shaft and looking at how it deforms, then formalizing our assumptions by stating that we're going to say that these things occur. The warping is constant as a function of x and y. In the z direction, the warping is the same everywhere along the shaft. Our in-plane displacements are now a function of where we are in the plane, but not a function of how far down the shaft we are. Okay, solving the problem now just means we need to find phi. Okay, we don't know what it is. We need to find it. Let me put up a set of examples here. Let's look at again, this is that same arbitrary cross-section that we saw previously. What do we know? Well, we know that our stress boundary conditions need to be satisfied. In this case, on a lateral surface of our shaft, as I twist this, what's going on in the middle of the shaft? Is there a traction boundary condition there? Well, sure there is. So if I were to draw a normal to that external surface, so that normal is shown here. Let me go ahead and zoom in on this for just a minute. That normal is shown normal to the surface. So n is now a surface normal. Obviously, it has components in the x and the y direction. We can also define an angle between nx and ny. And just due to, simple geometric arguments, the angle eta, which is present here, is the same as it is present here. So we can relate how much for any given unit length in this ultimately can be thought of as a tangent normal coordinate system. So you have a normal direction n, you have a tangent direction s, and the relationship between n and s now is a function of the surface normal, which can be related ultimately to this angle eta as well. Okay. Obviously, what we have, based on what we've seen so far, is that the traction components, here I'm writing them as Tx, Ty, and Tz, are going to be equal to the stress tensor dotted with the normal vector. The stress tensor, we know many of those components are 0. We identified the 4 strains that were 0, consequently the 4 stresses that are 0. we still have 2 stresses remaining. It looks like 4, but it's symmetric, so there's not 4 unique. There's only 2 unique. So tau xz and yz are the unique stresses that are remaining, and we have these 2 normal vectors, nx and y. Okay, it's pretty easy to actually calculate that. I'm just bringing this equation forward from the prior slide. Now I'm going to say that Tx is going to be equal to the first row dotted with the first column. Ty is going to be the second row dotted with the second column. Tz is going to be the third row dotted with the third column. We see the first 2 are both 0. I'd say that's relatively obvious. And the last one is going to be Txz nx plus Tyz ny. So that's what we're seeing here. And now, like we did before, we recognize that these stresses can be replaced by the Prandtl stress function phi. So this now becomes d phi dy nx minus d phi dx and y. Nicole asks, does lateral surface of the bar mean the top surface? No, it's not. It's not a top surface necessarily. This is any surface not along the axis. So it's really a transverse normal surface. So when I say lateral, it could be in any direction as long as it's on the outside surface and not along the z direction. Okay, so if we look at what this normal vector is, it has 2 components. We know there's no z component of this particular normal because the z axis is aligned with the long axis of the shaft. And if we went through and just examined the mathematics of it, in fact, I think I will, just to give you one more look at it. Here, again, you can see that the angle eta can be related to the normal. They are obviously directly related to each other through trigonometric arguments, and that relationship is given by this equation. So I'm saying 1 times sine of eta, and what does that mean? Again, we're assuming that the normal n is of length 1, and then the angle is simply going to be, the hypotenuse times the sine of the angle. So that's 1. Hypotenuse in all these cases now is 1. So 1 times sine of eta is the normal component in the x direction. 1 times cosine of eta is the normal component in the y direction. And, oh, by the way, this can be related to the derivative of y with respect to s, or the derivative with x with respect to s. So this is just a transformation between a normal and a tangent normal coordinate system, Sn, and an xy coordinate system. I think it's relatively straightforward that that's something that you guys have seen many times, I'm sure, in the past. So what we're developing is a change of variables. We're moving back and forth between Sn and xy. And once we've done that, we can now write the z component of the traction vector, t sub z, as being equal to d phi dy dy ds plus d phi dx dx ds. And, oh, by the way, this is equal to this, and that's just by the chain rule. Okay. In fact, the chain rule takes us from the bottom equation to the top equation, so sort of reversing the chain rule brings us back to this equation. Okay, let me pause there because I know that can be a little bit tough to to kind of chew on all that at one time. Happy to take any questions that may have arisen while we've gone through that. These are essentially just geometric arguments now.
Just algebraically, why isn't it 2 d phi ds at the bottom on 37?
Yeah, you'd have to go back and look at your chain rule definition. Think back to your calculus days, right? So the full derivative of something with respect to, I would just be restating the same thing over and over again. The very definition of the chain rule is that it's not, there's not two of them there.
Gotcha.
Okay, so Nicole says, can you explain again how you go from sine to dy ds? Yeah, I can. So I'm going to have to zoom in here. Okay, so if we have a, again, what this is a tangent normal coordinate system. So these are unit vectors. So the vector n has length 1 and the vector ds has length 1. Really, I should say the vector, really what you should be thinking about, this is dx, dy, and ds, okay? Small differential lengths where now ds ultimately has a unit length in the space that we're talking about. And you can relate the change in position in y to the angle eta and the unit length ds. And so that's just either sine or cosine, depending on whether you want to talk about dy, which is sine, or dx, which is cosine. Okay, so all of that being said, we need to circle back to this idea of a traction vector on a lateral surface of this thing. Okay, keep in mind I'm torquing the end of the shaft like so. What is the traction vector in the middle here on the exterior surface?
Would it be 0?
Yeah, it sure would. Why? There's nothing applying a stress to any of those exterior surfaces. Now, it would be a little bit different if I were grabbing it physically like this and then applying a twist, right? But for the purposes of the area between my hands, it's still traction free. And really, that's what we're analyzing right now is the area between my hands. We're not so much concerned about how the torque is applied as that it is applied in a resultant sense. You know, this is the same argument that we said we're going to treat the beam resultants as being the total force at the end of the beam, as opposed to looking at the actual stress at a point in the beam. Now, of course, you can calculate that. We could, but that's not what beam theory strives to achieve, nor is that what shaft theory strives to achieve here. Shaft theory is really nothing but beam theory applied to torsion problems. Anyway, so I don't remember who said it, but somebody said 0, right? So the traction vector is 0. So actually, let me go back one slide. So all of these components, tx, ty, tz, all 0. By this multiplication, we said, yeah, that checks for tx and ty. And now we're applying tz is equal to 0. And so when tz is equal to 0, we're going to have to say that this equation here, that is equal to 0. Okay, so the derivative of phi with respect to the s direction is equal to 0. the derivative of phi with respect to the s direction is equal to 0. That means along this outer surface, as you go from point to point around the circumference of the shaft, phi is a constant. Phi does not change as you move around that circle, or whatever that surface is. Okay, why is it a constant? Well, because we integrate phi with respect, we integrate d phi ds with respect to s. We get phi is equal to a constant. That's simply the integration constant. As a general rule, I would say, unless you've got a pretty compelling reason to do otherwise, and you will potentially in other courses at other times, but for our purposes, we're going to just assume that it's equal to 0. Okay, and it functionally won't impact the remainder of our discussion for today. So what have we done? Well, with respect to the Prandtl stress function, which is still unknown, we don't know what it is, but what we do know about it is that there's a boundary condition on the exterior surface of our shaft that says phi is a constant, and if phi exists, it satisfies equilibrium, and that's great, right? We're happy. Of course, it doesn't really do us a lot of good unless we actually know what phi is, because ultimately what we want to know is what are the stresses. We don't want to know what phi is. We want to know what the stresses are. Okay, so we still have a little bit of work to do to get those stresses out of our theory. I will make note of the fact that this obviously is going to be related to the applied torque, and you'll see that here in a few minutes. Okay, let me see here. I think since it is now 11 minutes to the hour, we have 1 minute. It's probably a good place to stop for today. I'll hang out for a few minutes to answer questions about this lecture or anything else that might arise. What is today? Today's Thursday, so I hope you have a good weekend. And I will see you back on Tuesday, if not before. Have a great day, guys.